Okay, good afternoon. So yeah, my name is Arnaud Mahieux. I'm working at the Royal Belgian Institute for Space Aeronomy, and I'm going to talk today about minor species in the Venus mesosphere from SWAR on board Venus Express, detection and upper limit profiles of this list of gases. But first of all, I'm going to give you a short introduction about Venus. So here on the right-hand side, you have the first image that was taken by the VMC camera on board the Venus Express spacecraft. This image is in the UV. And there, actually, you see the terminator that I'm going to talk a lot about today, and you see the clouds that actually all completely cover the Venus from pole to pole. So the main species of the Venus atmosphere is CO2, 96.5%. It is uniform. When you go up in altitude, above an altitude of approximately 110 kilometers, CO2 gets gradually replaced by CO and oxygen because of CO2 photodissociation. Another fact about Venus is that it's a very dry planet. There is a very low water quantity, and that the ratio between HDO and H2O is approximately 140 times larger than on Earth, meaning that a lot of water has escaped during the Venus history. And then the clouds that I talked at the beginning are mostly made of H2SO4 droplets, meaning that we have very big sulfur. We have lots of sulfur compounds everywhere in the Venus atmosphere and also above the clouds. And then you have also halogens, HCl and HF present in the atmosphere. Okay, so about the atmospheric structure. So here on the right, you have temperature as a function of altitude. You have the pressure scale on the right. And you have a mean temperature profile. Actually, it's been very smooth. We're missing a lot of details in this one. But if you look at the bottom, between the surface and approximately 35-40 kilometers, you have the troposphere, which is up to today mostly unknown region. It is very hard to observe because of the thick cloud layer, which is above, and that is the goal of the future Envision mission from ESA that's supposed to be launched in 2032. We know that there are very high temperatures and pressure. The temperature at the surface is about 750 Kelvin. The pressure is 92 bars. And we also know that there are very low winds at the surface. Above it, covering the troposphere and the lower mesosphere, you have the cloud layer extending from 35 more or less to 65 kilometers. So it is made of H2SO4 droplets, hydrated, and this cloud layer is in retrograde superrotation around the planet with winds of about 300 kilometers at the cloud top, so at 65 kilometers of altitude. Then you have the mesosphere. That's the region I'm going to focus on today, which is a transition region between the troposphere at the bottom, the thermosphere above. So you have complex wind patterns in that region, and you also find aerosols coming from the cloud layer. And then finally above it, the thermosphere. From above about 120 kilometers presents large differences between day and night, and there about the circulation you have a subsolar to antisolar circulation. So to study it, our institute, BIRA, developed the SWAR instrument. SWAR stands for Solar Occultation in the Infrared. It was on board the Venus Express mission from ESA that flew to Venus between 2006 and 2014. So SWAR was using an initial grading spectrometer combined to an AOTF. It was working at very high orders between 101 and 194. It was sensitive in the near infrared between 2200 and 4400 wave number, and at the time of launch it was the spectrometer with the best spectral resolution, varying between 0.11 and 0.21 wave number, and also a very good spectral sampling between 0.06 and 0.12 wave number, increasing with order. So SWAR had also, since we were looking at the sun, we had a very good SNR, varying between 1,000 and 3,000 depending on the order. And it had the capacity to measure simultaneously 4 diffraction orders during an occultation, meaning that we could either target 4 different species or the same species but at different altitudes. SWAR was only performing solar occultations, so all the the data I'm going to show today are always at the terminator, but covering all latitudes from pole to pole. And we have about a bit more than 800 solar occultations that were taken during the whole mission. So you will see that actually in our spectra, the species listed here have a clear signature. So we've been working a lot on CO2, so the main species from which we could derive temperature profiles. This is what you see here. So these are all the CO2 profiles as a function of altitude, number density here, and the temperature that we derived considering the hydrostatic equation. SWAR could also measure CO. Water and heavy water, also halides, HCl and HF. Here you have an example of the mean HCl volume mixing ratio as a function of the pressure, and also to aerosols. One of the striking facts about the Venus mesosphere and thermosphere is the large variability that we observe in actually the main gas CO2, but also in all the other ones. You will see that in the coming slides. So in this work, I'm going to talk about other species that we could detect, which are sulfur species listed here. Also, we could detect ozone and HO2. We have possible detection of H2CO, HCN, and NH3. And the 4 species listed here at the bottom, we have no clear detection, so we are only providing upper limit values. So here on the right, you have all the lines of Hytron between 2200 and 4400 that I multiplied by typical volume mixing ratios on Venus. You have the CO2 bands here. You have water over here, HDO over here, HCl lines. These are all the gray ones. And the species that we are targeting in this work are the one here in color. And on this graph, actually the red line that you see here would correspond to the approximate SWAR detection limit. So you see that all these species would have signature very close to the noise. So because of that, we had to design a special procedure in order to derive the concentration of those gases and try to detect them in our spectra. So the technique that we are using is based on statistics. We're trying to reduce the chi-square in the spectra. I'm going to explain that in the next slide. And we checked that our method works by building synthetic spectra to which we knew the VMR of the different species that we tried to retrieve, adding noise equivalent to SWAR, and then trying to retrieve them and compare with the a priori. So here at the top right, you have an example of a data set taken during a solar occultation. You have the wave number as a function of transmittance. All the lines that you see, so each line corresponds to a spectrum taken at different altitudes. The lines correspond to CO2. And the goal is to see whether there is NH3 below those lines. So for each of those spectrum, what we fitted is the slant density. And actually we did 2 different fits, one considering CO2 and NH3, and the second one considering only CO2. And then we applied criteria to decide whether we have a detection of NH3 or not. We are comparing actually the chi-square of the fit and seeing if by adding NH3 to the fit, we reduce the chi-square by either 5, 10, or 20%. We also compare the retrieved slant column density of the minor species, so in this case NH3, to the upper limit of detection computed from the noise in the spectra. We check that the correlation between the fit considering both species is larger than considering only CO2, and also that the uncertainty is smaller than the retrieved slant density, and we're only considering transmittances larger than 0.1, so all the ones here above. And in case we would have more than one detection during an occultation, we use a Tikhonov regularization method to compute the local number density and its uncertainty. So here is an example of those detections. The first one is regarding SO3. So here on the top left, you have in black the measured spectrum by SWAR, transmittance given here. You have the wave number here at the bottom. And then you have the two fits that we performed. So in this region, there are actually three gases absorbing, four gases. You have CO2, HCl, and H2O, and SO3. So the first fit in blue that actually you can hardly see because it's below the other colors is a fit considering those four species. Then we did a second fit considering only CO2, HCl, and water. And then S3, the green one is the same as S1, but we just put the number density, the slant density, sorry, of SO3 to 0. If we go to the middle here, so here, and you have between parentheses the correlation coefficients between all the fits and the measured spectrum. Here in the center, you have the residuals from the fit with the definition given here. So in black, you would have actually the signature of SO3. Then in blue, you have the residuals of the fit considering SO3. In red, not fitting without SO3. And then finally, the one from is the same as S1, from which we just put SO3 to 0. The black region here, so then we apply the criteria I defined in the previous slide. We only apply them in the region in black, in white and yellow, sorry, not in the black region because we have a worse signal-to-noise ratio in those regions. And the yellow regions are the ones where we have the signature of SO3 being larger than the noise. The noise of SWR is given here as the dashed line, and where also M-S1 is smaller than M-S2, meaning that actually we have a better fit considering SO3 here. At the bottom, it is the same as the residuals here, but dividing by the noise. Why I plotted this is because here on the right, I'm considering the distribution of the residuals divided by the noise, and just assuming they are Gaussian and fitting a Gaussian to it. The full width at half maximum of the Gaussian is given here, and it's a certainty. Doing this considering S1 and S2, and it's just showing that this one is narrower than the second one. Another example here about ozone that we heard a lot today. So in this spectrum here at the top, actually we have also four species absorbing HCl, water, CO2, and ozone. We do the same fits S1 and S2. You have again the yellow regions where where the noise is smaller than the signature of ozone, and also where the fit is better considering ozone than not considering ozone. So here are finally the results. Considering the whole data set. So first, the first species we consider this SO2. You have the volume mixing ratio of SO2 as a function of altitude. All the colored dots are our retrieved values, and all the black either symbols or lines correspond to values from the literature. You see that we are in pretty good agreement with the literature. You also see that there is a trend here above 80 kilometers. This is probably an artifact of the method, just because we cannot detect points that would be in this region. But that was observed also by the speaker, another instrument that was doing the same retrievals, but in the ultraviolet. We could also detect OCS that was previously measured in the Venus mesosphere. You have the black line here. So our values vary between a few ppbs up to 1 ppm. Also with that trend as a function of altitude, but which corresponds probably to spikes of OCS in the atmosphere. I said at the beginning, the Venus atmosphere is very variable. You can have variations up to 2 to 3 orders of magnitude of all the gases, the minor species. Then we have also detection of SO3 given here with values varying between 100 ppbs and 10 ppm. We also detected for the first time CS in the atmosphere in the upper atmosphere of Venus, also with values varying between 0.1 ppm and 100 ppm. CS2, for which actually what was measured, that order in which CS2 is absorbing was only measured a few times, but we had one detection given here. Ozone also that we could detect. There was a previous measurement from UV given here. You see that we are 1 to 2 orders of magnitude larger than this. This might be due to, this is probably due that we are again only measuring spikes, excess of ozone due to the activity in the atmosphere. And then we have H2CO, but that one needs to be confirmed. We're doing further analysis of the spectra to confirm that we really see it. NH3, the same, which might be a bit problematic. So we really want to be sure of that one. HCN and HO2. That takes me to the conclusion, saying that I hope I showed you that SWAR is also sensitive to, amongst the other gases, to the list given here. We have possible detection of HCN and H3 and H2CO to be confirmed. We have no detection of the gases listed here. SO3, OCS, and ozone had been measured before in the Venus mesosphere. All the other gases, these are new measurements, and SO3 had only been detected in the cloud layer. Thank you very much.